Hello and welcome to the final vodcast on 4.4 wave behaviour, where we'll be looking at interference, just standing waves to go, as part of the SL topic for waves. The parts we're going to be looking at today of the subject guide are interference patterns, in particular the double slit interference. We're going to be defining what we mean by path difference, and we're going to be quantitatively describing double slit interference intensity patterns. Notice the difference here, and we'll be making a point of contrast with single slit. For the standard level, you're only required to qualitatively describe diffraction patterns, where you are required to quantitatively describe double slit interference. In other words, you need to be able to actually do some calculations regarding double slit interference. But what do we mean? Well, as an introduction, let's take this kind of scene here, where you've got two people making some waves in otherwise still waters. And we'll just presume that they're kind of identically making those waves, and those waves are going to spread out from the points at which they're created, and they are going to interfere with each other. You remember we looked at superposition, so as the waves pass through each other, the displacements will add or subtract negatively. If you have two peaks together, two crests together, you'll get double the displacement, and if you get a peak and a trough, a crest and a trough going together, then they will cancel out. So these waves are identical wavelength, identical amplitude, etc. And you'll get this interference pattern combining the two. But what about if instead of having the two waves in the middle, we've got them here at the side? This is Derek from Veritasium, who made this video, which I'll link to. But here's a still from that, and he's taken two. You can just see one here at the bottom, and one's kind of behind his head. Two sort of dippers or something, two objects. He's making a pattern in the water. Again, he's making identical waves, and here you can actually see the visualization of that pattern. So whereas previously it sort of showed this big sort of chaotic area almost, here, yeah, between the two patterns there is that kind of chaotic area. But once you get away a little bit, you'll see there's actually a much more regular pattern occurring. And indeed, we can identify these areas here where we have constructive interference. So anywhere kind of along this line, we're having constructive, or these lines, we have this constructive interference. Peaks are adding together, troughs are adding together, so you have double the amplitude of waves in these places all along them. And similarly, a little bit obvious, or more obvious, more clear to see in terms of more limited geographically, so to speak, we have these zones of destructive interference where the waves are cancelling out. So taking them together, we have this characteristic pattern, this interference pattern of zones of constructive interference interspaced by zones of destructive interference. And that's what it looks like from a two-dimensional perspective. Constructive interference separated by destructive interference. Here's kind of a top-down view of that, just using the same kind of symbology that we were looking at in the previous topic. So two slits. So previously the two examples we've had involved oscillators. Now let's say we don't have oscillators. Instead, we have two slits in a barrier. We have a uniform wave coming about. So uniform meaning that by virtue of having a single wave source here, we have the same wavelength, the same wave speed, and they are in phase. So they are always leaving as peaks or troughs together. They interfere together. And here's another example of that, taken from the Curiosity website. So you have a wave source here going to two slits. It's coherent, it's in phase, and then you have these two interfering together, and that's kind of a top-down view. You have these, again, you'll get these zones of constructive and destructive interference. And when that matches a screen, because now we've moved to a light source from a wave source, you'll get this pattern of light and dark. Now that's key. That's really key here. This is the classic interference pattern. By the way, we were looking at water waves, now we're looking at light waves. Sound waves do this as well. This is one of those examples of one of those universal wave phenomena. Interference, diffraction, reflection and refraction are the things that all waves, or at least all two-dimensional or more waves, do. So this characteristic pattern here is zones of constructive interference where the waves are adding together, and interspersed zones of destructive interference where the waves cancel out. So again, this is what you'll see on a double slit. Now, you might be able to see in this sort of real life example here, but we've got kind of two different patterns going on, because we've got this kind of overall large pattern and then this interspersing of this small pattern. What we're interested in is the smaller pattern. The larger pattern comes because, as you saw in the previous podcast, single slits also actually produce a pattern of light and dark. In fact, we can look at that here. So at the top is what would happen if you're looking through a single slit showing a basic diffraction pattern. Again, high-level students have to actually mathematically explain that. For standard level, it's enough just to be able to view it and describe it. See the last podcast for more details. And underneath it, we have a double slit. Now, the width of the two slits is the same as the width of the single slit. So you have the same basic diffraction pattern, but superimposed on that, you have this more detailed, if you like, diffraction, interference pattern, as it's called, or interference fringes is the wording used here. Now, we are required to try to quantitatively explain this, and that's what we're going to do here. You also remember that we have the term path difference, so we'll be introducing that. So this is a top-down view. Light waves makes more sense here, although it could be, say, water, or it could even be sound waves. We'll have a double slit, and these are producing coherent, same wavelength, same phase sources of waves, light waves, water waves, whatever. And at the end, we will get, as we've just said, this sort of double slit interference pattern. We're just interested in these alternating patterns of bright, dark, bright, dark, bright, dark. Why are they happening? And why are they not just why are they happening overall, why are they happening in those specific locations? Well, the key here is to take a line or two lines and draw it from the center of each slit to the screen. And here is kind of the default position, which is where you have the right slit to screen path and the left slit to screen path. And because they're meeting in the middle between the two slits, those two paths are the same length. Now we measure the length of these two paths using a concept called the path difference, because we're not so interested in their actual lengths, we're interested in how they compare to each other. And rather than use units of meters or centimeters or whatever, we're going to use units of wavelengths. So how many complete wavelengths is the right slit to screen path? How many wavelengths, complete or fraction of a wavelength, is the left slit to screen path? And then if we subtract one from the other, what do we get? And in the situation we've just drawn here, we get 0. We get a path difference of 0 because they're the same length. Now I've taken away the image, and instead I'm going to just put a C to illustrate or indicate that we have constructive interference at that point. Now if we move along from that point towards the right in this case, then initially what's going to happen is that the right slit screen path is going to get shorter and the left slit to screen path is going to get longer. And the path difference will no longer be 0. It'll get bigger. Okay, if I take the longer one, which is going to be the left slit to screen, and subtract the right one, I don't get 0 anymore. I get a bigger number. But at some point along the screen, that path difference will be exactly 1 wavelength. When that path difference is 1 wavelength, we will have again constructive interference. And the reason we have that is because again, we'll have a crest arriving with a crest, or a trough with a trough. So we'll have constructive interference, will have doubling the amplitude at that point. And we can do it further. Again, moving towards the right, the two distances will change. And again, the difference between them will get, bigger. And again, at some point, that path difference will be equal to 2 wavelengths. And again, because they are going to both arrive crests together or troughs together, one will have taken 2 wavelengths longer to get there, but they'll still arrive crests together or troughs together, peaks or lows. Then again, we'll have constructive interference. And again, we can move further along the screen and we'll find another point at which we have a path difference, this time of 3 wavelengths. So hopefully you can see the pattern here that whenever we have a path difference in a whole or integer number of wavelengths, we will get constructive interference. And in between those points, halfway between them, we'll get destructive interference when the path difference is half a wavelength, or 1.5 wavelengths, or 2.5 wavelengths, or 3.5 wavelengths. When it has a half wavelength component, we will have destructive interference. So we have 2 rules. The rule for constructive interference is that the path difference is n lambda, where lambda is the wavelength and n is some integer number, including 0. And destructive interference is where the path difference is n lambda divided by 2. Okay, so half, 1.5, 2.5, 3.5, etc. So we now can quantitatively predict when you will have constructive interference. You will have constructive interference when there is a whole wavelength number of integer number of wavelengths path difference. And if we keep everything the same, if we keep the slit separation the same, if we keep the distance from the slit to the screen the same, etc., etc., but we change the wavelength of the light from red to green or to another colour, then the position of those, the interference fringes will change, because different points on the screen will give you different path differences for the different colours. Okay, so we have looked at interference patterns, particularly double slit interference. We have looked at defined path difference, and we are now able to quantitatively describe double slit interference intensity patterns. Thank you very much.